This is a gecko. They have an amazing ability to climb. They have feet that can stick to almost any surface, and they seem to effortlessly defy gravity. But their feet aren't sticky. They can lift their feet easily as they walk, and they don't have any suction cups on their toes. So how is this possible? Amazingly, it has taken scientists an incredibly long time to solve this puzzle. But the answer has to do with intermolecular forces. Alright, so as the name implies, intermolecular forces are the forces that exist between molecules. So we've already discussed covalent network solids and ionic solids and metallic solids. Now we're focused on molecular substances. And what holds molecular substances together are intermolecular forces. And these intermolecular forces are governed almost entirely by charges and how charge is distributed in a molecule. So we need to be really concerned about whether or not charge is distributed in a molecule equally. Now, the first time we thought about whether or not charge was distributed equally was when we looked at the covalent bond. And so if I imagine a bond, again, between my fictional atoms X and Y, if X and Y are significantly different in terms of their electronegativities, then I know that the electrons in this bond will be unevenly shared. And that will create something called a dipole. So in this particular case, I'm indicating the X as being partially negative and the Y as being partially positive, which means that in this hypothetical bond, X is the more electronegative element of the two. And so this creates a polar bond, and this is a dipole, or two poles, one negative end of the bond and one positive end of the bond. Now, this is an important thing to wrap our head around because it is precisely this disparity in charge distribution that will cause attractive forces between this molecule and other molecules like it. They are essentially behaving like little magnets where I've got a positive pole on this end and a negative pole on that end. So another molecule or another copy of this XY species will likely orient itself like so, such that there's an attraction between the two molecules from the positive end of one to the negative end of the other. This is fundamentally what intermolecular forces are all about. The only thing we really need to do now is decide how polar are molecules that have a more complicated structure than just a single bond, and then what are all the different types of options for these molecules to interact with one another. Here is a handful of molecules with the electronegativities of each atom indicated. We're also indicating these arrows which point in the direction of the atom that is most electronegative for each bond. This is an indication of a polar bond. And so if we look at the simple example of HCl, we can see that there's a reasonable difference between the electronegativities of the two atoms, and so we call this a polar molecule. There is a negative end and a positive end, typified by this arrow. Likewise, we can look at the other molecules to see similar sorts of trends. For example, in CH3Cl, we notice that one of the bonds is relatively polar, the difference between carbon and chlorine, but the others not so much. And so there is a net polarity in the direction of this electronegative chlorine atom. A similar effect can be seen with ammonia, NH3. We know from our studies of ammonia in the past that there's a lone pair of electrons here. And so the polarity of all of these bonds in this trigonal pyramidal structure are all pointing in the same direction, which is up near the top of this molecule. And we would also predict that this molecule is polar, because the sum total of all of those polar bonds results in a net dipole for this molecule. So we say that the molecule itself is polar. Now, this is to be contrasted with something like carbon tetrachloride, or CCl4. Yes, each and every one of these bonds is polar, but all of them are effectively counteracting each other. And whenever you have a scenario where all of the electron domains around the central atom are bonding domains, and they all have the same exact polarity, then the result is a nonpolar center, and in this particular case, a nonpolar molecule. The electronic charge disparity between these two atoms is canceled by the disparity between the other three, and vice versa. We can see the same effect for BF3. Notice that each of these bonds are in fact polar to a significant extent, except they all pull in opposite directions. Again, this is a central atom whose domains are all bonding domains, and every one of these bonding domains is equivalent. Therefore, overall, the molecule is not polar. So if I need to determine if a molecule is polar or not, I'm really primarily thinking of two questions in particular. One is, does the molecule have polar bonds at all in the first place? And if it does, is that molecule symmetrical? In other words, are all of the electron domains around a particular central atom equivalent? If I do have polar bonds and I'm not symmetrical, then I can be confident that my molecule will be polar. And now that I'm able to diagnose whether or not a molecule is polar, let's consider what happens when we bring polar and nonpolar molecules together. What types of forces exist to hold these systems in place? So if intermolecular forces are all about charge and charge distribution, then I would expect that some of the strongest attractive forces should be at play between fully charged species. This is the first type of intermolecular interaction I'd like to talk about, which is called ion-dipole interactions. In other words, we're going to have an ion interacting with a molecule that has a dipole. So for example, think of something like salt water, right? Salt is composed of ions. Let's take a sodium ion as an example, and that's a positively charged species. It's a cation. It would want to orient itself near the negative end of the dipole in another molecule. Now, water has a structure like so, with a couple of lone pairs on the oxygen atom. And because the electronegativity disparity between oxygen and hydrogen is somewhat large, these are each polar bonds. So I have polar bonds, and my molecule is not perfectly symmetrical because not all electron domains look the same. I know that this molecule has a net dipole. In other words, it's polar toward the direction of the most electronegative atom. So my water molecule has an overall dipole associated with it that I can indicate like so. And so the negative end of my water molecule is near the oxygen atom, and the positive end is down near the hydrogen atoms. As such, I can expect a very strong interaction between the fully positive cation, which is the sodium ion in this case, and the partially negative oxygen, which is the negative end of the dipole of the water molecule. So this type of force is known as an ion-dipole type force. And to see it, or for this force to be present in your system, obviously you need to have an ion. So this is the type of force present in dissolved solutions of salts and other ionic species. So ion next to a dipole creates an attractive force between these two that's known as the ion-dipole force. Now, if I don't have a fully charged species, a cation or an anion, in my system, then I really can't have an ion-dipole type interaction. But if I do have molecules that contain a dipole, then they can attract one another via a dipole-dipole interaction. So imagine something simple like the hydrogen fluoride molecule, for example. It's quite clear that this will have a dipole, in which case the fluorine will be the negative end of this molecule, the hydrogen is the positive end, and so we can often write the dipole like so. If I have multiple copies of this molecule, which in all cases I would, then I can be sure that these molecules will orient themselves such that the negative end of one is pointed toward the positive end of the other. Just like if I had a series of magnets, they would all line up and attract one another in the order of their dipoles. And so there is an attractive force that exists between these neighboring molecules to hold them in relatively close proximity to one another, and that force is known as a dipole-dipole force. Now, the strength of that force is proportional, obviously, to the strength of the dipole. In other words, if I have a very strong disparity of electronegativity between my atoms here, which creates a very large dipole, very large disparity in electronic distribution, then that means that this positive end is actually quite positive. And likewise, this negative end is actually quite negative. And therefore, the interaction between these two, in other words, the dipole-dipole interaction, would be very strong, comparatively so. Now, in contrast, it could be relatively weak if the difference in electronegativity between these two atoms is relatively small. So all of these types of intermolecular forces have ranges associated with them. And that's fundamentally because all of these intermolecular forces are associated with charges. And these charges all have ranges associated with them. Because, of course, the difference between electronegativities in several atoms can be wildly varying. Now, what happens in a system where we have a molecule with a dipole in close proximity to a molecule without a dipole? Let's use the iodine molecule as an example. Clearly, the iodine molecule has no dipole associated with it. Each atom is identical. They are equally proficient at pulling electrons toward itself, and so this is an equal sharing of electrons, and there is no net negative end or positive end in this molecule at all. But of course, we know that in HF, there certainly is a disparity in how the electrons are distributed. So there is a negative end associated with the fluorine here and a positive end associated with the hydrogen. So should we expect any sort of attractive force existing between these two species should they come into contact in some solution? Well, the answer is yes, because of the fact that if in my leftmost molecule here, my hydrogen fluoride, I have an excess of electrons on this end. Now, if my iodine molecule approaches my hydrogen fluoride from this direction, then it's quite possible, in fact likely, that the electrons on this side of my HF will actually repel the electrons on the iodine molecule and force them over to the right-hand side of this molecule. In that relatively brief instant in time, I have induced a dipole in my iodine molecule. I do not expect that dipole to be strong, but it has been induced by virtue of the fact that there are electrons, an excess of them, if you will, on my fluorine atom. These electrons will cause the neighboring electrons to flee or repel and go toward the right-hand side or the opposite side of the neighboring molecule. So notice that if and when that happens, there is a slight dipole that is induced in our otherwise nonpolar molecule. And so the moral of the story here is that there is, in fact, an attractive force between these two molecules as a result of this induced dipole. I shouldn't expect this attraction to be very strong per se. I mean, there wasn't even a dipole in my iodine molecule to begin with. But the point is that it isn't zero. There is an attractive force that exists between these molecules. Now you might ask yourself, what evidence do we have that tells us that this force exists? And what evidence do we have that helps us measure the strength of these various forces? Well, we're going to get into that in quite a bit of detail over the coming weeks of this class, but if you give it some thought, I think you'll realize that many of the measurable properties of solutions of these compounds are directly correlated to these intermolecular forces. For example, if I want to boil something, if I want to boil a solution, by definition, I want to pull apart the molecules in the solution. So for example, if I want to take these molecules and put them into the gas phase, for example, that will require me to isolate the individual molecules. Separating them to great distances. And if there is an attractive force that had existed between them, then doing this will cost energy. And so we all know that boiling systems often does cost energy, and boiling different solutions takes different amounts of energy. And that's just one of the various ways that we can collect experimental data that help us to verify these theoretical ideas. So yes, a induced dipole force is a very relevant, very real force that can exist when we bring a dipole in close proximity to a molecule that isn't polar. All right, so what do we do in the case where we have no dipole whatsoever? Now, if iodine is by itself, or should I say with only other versions of iodine, or other molecules of iodine, there are no dipoles anywhere to be found. It's difficult to induce a dipole in another molecule when you yourself don't have a dipole at all. So the question here is really, is there any sort of interaction between these neighboring molecules? Is there such a thing as induced dipole? It sounds weird to even say. In fact, this is not really what we call it anyway. A force that may exist between these nonpolar species, at least in this particular case, we often give a name: dispersion. You may have also heard of London dispersion, that's the same thing, or van der Waals forces is another word often given to this phenomenon. What is it though? Well, dispersion is a force that exists between all molecules, and that's an important distinction. I'm picking on nonpolar molecules here, but once I define what it is, I think you'll realize that in principle, dispersion is present always, regardless of whether my molecule has a dipole or not. In a series of molecules like you're seeing here, so iodine, we have a lot of electrons. And those electrons spend a lot of time moving around the molecule itself. Because these electrons are dynamic entities, they are moving, it is statistically possible, although, maybe we wouldn't anticipate it being likely, but it is statistically possible that as the electrons in this system are propagating through space and time, that there might be an instantaneous moment, ever so brief, where the electrons happen to be unevenly distributed. In other words, as the electrons are migrating around this molecule, generally in a symmetrical way, at any instant in time, if we were to freeze this, take a snapshot of where all of those electrons were, it is certainly possible that the net result here is that most of the electrons may be instantaneously unevenly spread out. And maybe, for example, we might find that most of them happen to be over here on the right-hand side of the molecule. If in that brief instant in time, those electrons, or at least the majority of the electrons, were found unevenly or predominantly on one side of our molecule, that would be what we call an instantaneous dipole. It's gone just as quick as it arrived, but the point is it was there in the first place. An instantaneous dipole arising in our molecule. Now, if and when that particular instantaneous dipole happens, it then has the ability to induce a similar effect in its neighbors. So this instantaneous dipole that arises spontaneously in a particular molecule within our system will then spontaneously induce a dipole in its neighbor for the same reason that we saw induced dipoles in the past. A dipole, or in other words, a net positive charge here on this end of the molecule, will cause electrons on this molecule to draw toward it. Electrons are attracted to a positive charge. So this instantaneous dipole then induces another instantaneous dipole, and at that brief moment in time, there is an attractive force between these two species. I would not call it a dipole-dipole force. You could potentially think of it as an instantaneous dipole-induced dipole. But that's a lot of words. We tend to just call this type of force dispersion. Not to mention the fact that this dispersion type interaction can exist between all molecules. Even if I have a permanent dipole, there is still a chance that over time, my electrons can become even more unevenly distributed through statistical chance, which then strengthens the amount of my dipole and then strengthens the amount of my interactions with my neighbors. So dispersion is an ever-present reality in all types of molecules, even nonpolar ones. In fact, in nonpolar ones, it's special because dispersion is the only force available to attract these neighboring molecules. Now, do I expect this interaction to be particularly strong? Well, no, but there's an important caveat to that statement. Iodine, which is the example that happens to be on the screen right now, actually exists as a liquid. And the reason why that should be surprising to you is, of course, because iodine is nonpolar. Nonpolar molecules like iodine, as we've seen, don't tend to have very much attractive forces to its neighbors. Let's consider as another example something like hydrogen. Well, we know that the hydrogen molecule should also be nonpolar, and I think we're also pretty familiar with the concept of hydrogen gas. Why is hydrogen a gas? Well, it's a gas because hydrogen doesn't interact very strongly with the neighboring hydrogen molecules. The reason why it doesn't interact very strongly with its neighbors is because it's not polar. It doesn't have an uneven charge distribution, and therefore it doesn't have access to all of those types of intermolecular forces that draw molecules together. So in the absence of forces that draw molecules together, there's nothing holding a hydrogen molecule next to its neighbor. And if there's nothing holding those molecules together, they float off into space as a gas. And this is true of pretty much most of the diatomic species you've heard of. Things like oxygen, O2, nitrogen, N2. All of these species are gas phase. And for good reason. They don't have any strong interactions with their neighbors. They do have dispersion, though, but by virtue of the fact that those are gases, we can infer that the dispersion interaction isn't strong enough to hold many copies of these molecules together such that they would be condensed and we could see them as a liquid or a solid. But that's not true for iodine. Why would it not be true for iodine? Well, if dispersion is a statistical effect, in other words, It's just a simple outcome of the statistical likelihood of electrons moving in space and time. Well, if that's true, then iodine is a special case because of how many electrons it has. Iodine is element 53 in the periodic table, so that means I've got 106 electrons in an iodine molecule. That's an awful lot of electrons and therefore an awful lot of statistical probability for those electrons to be unevenly distributed. Also, when your atoms are that large, as we've seen in previous classes, they don't tend to hold their electrons very tightly. In other words, the electron cloud that is around the iodine molecule is very polarizable. It's very shiftable. It's not very tightly bound to the molecule. And so like a wispy cloud on a windy day, it can easily shift from side to side, therefore causing an instantaneous dipole. And so dispersion is an ever-present force, but in some species, it can be enough to actually hold those molecules together. And iodine exists as a liquid in its standard state. In other words, enough dispersion can be strong if you add a lot of it together. The other contributing factor to dispersion is surface area. So if we have long carbon chains that have a lot of surface area that can come in contact with other long carbon chains, they tend to have more dispersion interactions simply because there's more surface area for those interactions to occur over. Now, I could say that that's the full story, but of course I'd be lying. And the evidence that I need to show you to prove that is on the screen now. This is a plot of boiling points of a whole series of different liquids. You can see some of the obvious ones like the water molecule, hydrogen fluoride, ammonia, methane, so on and so forth. How this data is organized is by period on the horizontal axis. So if I look up a series that is connected, I see that the carbon has been substituted for silicon, which has been substituted for germanium, which has been substituted for tin. In other words, I've gone down the periodic table from carbon, silicon, germanium to tin. The next line is the same thing. I'm at nitrogen, then I go to phosphorus, then I go to arsenic, then I go to antimony. So this is the same series down the periodic table. To complete this series, I can look and I can say, well, I've got fluorine here, chlorine, bromine, and iodine. And then finally, I've got oxygen, which is water in this particular case, sulfur, selenium, and tellurium. Now, in terms of dispersion interactions, we can certainly see that if I focus on this part of the data, as the bulk or as the number of electrons in the system goes up, the boiling point goes up. In other words, it takes more energy to separate the molecules from one another. Now that makes sense. And generally speaking, the trend we would expect is that of starting low and building up to high. But I think it's fairly obvious in this particular diagram that there are three remarkable outliers on this image. Now, of course, those molecules all have dipoles, but so do many of the others in the series that they represent. Clearly, there is something very different about these species. They are anomalous and stand out and break the trend very, very significantly. And so it begs the question, what is going on with these molecules and potentially others like them that cause their intermolecular interactions to be so high? It must be true that the intermolecular interactions between neighboring water molecules must be extraordinarily strong. Otherwise, why would it cost so much energy? Why would it take so much heat to boil a sample of water? We don't often think about this because usually the only thing we've ever boiled is water. We don't realize that it is an extraordinarily anomalous substance. I'll go into some more detail about water in a future lecture, but for today, we need to understand why species like water, ammonia, and HF have such strong intermolecular interactions relative to what we would have expected. Yes, of course, they're all polar, and they all have dipole-dipole interactions, but there must be something extra, something else going on to amplify the effect of these intermolecular forces. The answer here can be found in the patterns of the various structures we observe who demonstrate this effect. It turns out that molecules that obey the following relationship, which is an atom bonded specifically to hydrogen, in the proximity of another atom, both of which are highly electronegative. So if X happens to be a highly electronegative element, something like oxygen or nitrogen or fluorine, then I can expect that the polarity of this particular bond will be quite high, of course, because hydrogen is not so electronegative. Likewise, if the nature of my Y atom here, or the species that is in close proximity to my hydrogen, is also an oxygen, a nitrogen, or a fluorine, then I've got essentially a perfect storm for a dipole-dipole interaction. In other words, I've put some very strong electronegative elements bonded to hydrogen, which will withdraw most of this density away from the hydrogen, and most of the electrons will reside on the electronegative element. This will cause a very, very polar bond with a positive end near the hydrogen. And if in the vicinity of that particular system, I've got another oxygen, nitrogen, or fluorine, another highly electronegative element, then I will have likely a significant negative partial charge at that position. This creates a scenario that is absolutely ripe for causing strong intermolecular interactions between these two species. This is known as a hydrogen bond. Hydrogen bonding happens to be an extraordinarily strong type of intermolecular interaction because it's essentially a dipole-dipole interaction on steroids. It's got the perfect arrangement of dipoles with the perfect atoms to create the strongest possible dipole-dipole interaction. Not only are X and Y extraordinarily electronegative, but hydrogen is nothing more than a proton with a single electron. So once that electron gets stripped, there is essentially a very, very attractive positive charge there with no neighboring electrons around it to repel an incoming negative charge. So it really is the perfect storm of intermolecular interactions, and this type of interaction happens to be exceptionally strong. And the evidence that we have to support this is not just in the boiling points of substances like this, but we see evidence of this strength in countless cases, predominantly in biochemistry, where hydrogen bonding is used to dictate the three-dimensional structures of proteins and active sites and receptors that we've talked about before, which governs so much of the biochemistry that we learn about. And so that summarizes the scope of intermolecular forces that we expect to observe in molecular substances. There are several different types, but the good news is that they are all fundamentally from the same phenomenon, which is an interaction between charges. So really the key piece of information here is how polar is our molecule? Because that level of polarity will dictate the level of intermolecular interactions it has with its neighbors. Now, we can do a lot more with polarity, but for now, what we need to understand are these various different types of interactions. Ions are, of course, fully charged species which can interact with dipoles quite strongly, and we see the range of their interaction energies are quite large. Dipoles, of course, interact with one another for the same reason, but not to quite as great an extent because, of course, they're not fully charged species, they're just polar molecules. Hydrogen bonding is a type of interaction we've just learned about, which is essentially a perfect storm, if you will, of electronegativities coming into play, which causes very strong intermolecular interactions. Dipole-induced dipole can be present when some nonpolar molecules are in the vicinity of polar molecules. And then finally, induced dipole, or more commonly referred to as dispersion forces, are forces that exist between all molecular species, but it's the only force that exists between nonpolar molecules, like, for example, the iodine dimer. Now, the range given here for these types of forces is large, as you can see, because of the fact that these dispersion forces can be strong if you have them in a large amount. Which brings me back to the gecko. It turns out that a gecko's feet contain millions of tiny microscopic hairs, which allow for an enormous surface area and close contact between the feet and other surfaces. This dispersion that exists between all substances is therefore amplified and ends up being incredibly strong. And now engineers are trying to harness this technology for a wide range of applications, like window washing robots and Spider-Man gloves. Very cool technology, and it's all chemistry.